Three-dimensional coordinate systems, level 9. In the previous video, we covered intermediate level examples that required the use of the equation of a sphere. Now we are going to go over two more challenging examples. Let's go over the first example. Find an equation of the largest sphere with center 5, 4, 9 that is contained in the first octant. This example builds upon the problems from the previous video. The problem is asking us to find the largest sphere with center 5, 4, 9 that is contained in the first octant. How can we figure this one out? Let's first think about an easier problem that is related to this one. Say we have a random circle that is placed in the first quadrant of a two-dimensional coordinate system. If we were trying to find the largest circle that is contained in this quadrant, one way we can solve this problem is by expanding the circle until it literally hits one of the two axes. If we allow this to happen, the circle will actually be tangent to one of the coordinate axes. It turns out that we will actually hit the coordinate axis that is closest to the center. In the three-dimensional case, if we allow this sphere to expand, as if we were inflating a ball or a balloon, it will end up hitting one of the coordinate planes. Similar to the two-dimensional case, the sphere will end up touching the coordinate plane that is closest to its center. Let's actually find the distance from the center of the sphere to each of the three coordinate planes. Recall from the previous video that since all three coordinate planes are perpendicular to one of the coordinate axes, finding the length reduces to just measuring the distance from the center to each of the coordinate planes along the direction of a single coordinate axis. This means that the xy plane is 9 units away from the center. The yz plane is 5 units away from the center, and the xz plane is 4 units away from the center. If we were to let the sphere expand, it will end up hitting the xz coordinate plane. If the sphere is allowed to expand beyond this plane, it will cease to be contained in the first octant. So the radius of the sphere is equal to 4. The largest sphere that is contained in the first octant with the given center is represented by the equation the quantity x minus 5 squared plus the quantity y minus 4 squared plus the quantity z minus 9 squared equals 16. The hard part of this problem was to understand the idea of containing the sphere in the first octant. It turns out that the shortest distance from the center to the coordinate plane limits how much the sphere will be able to expand and at the same time be constrained in the first octant. Alright, let's try the next example. Find an equation of the sphere with center in the xz plane and passing through the points P, Q, and R. Notice that in this problem, we are not provided with the center or the radius of the sphere, nor are we provided with the endpoints of the diameter. We are dealing with a completely different problem, not addressed in the previous videos. We are asked to find the equation of a sphere with its center located in the xz plane. All we know from this specific information is that the center of the sphere will have coordinates equal to h, 0, and L. Since we don't know what the x and z coordinates of the center are equal to, we leave them as h and L. In addition, we also know that k is equal to 0 because any point located in the xz plane has 0 as its y coordinate. Next, we are given 3 distinct points that are located on the surface of the sphere. We need to somehow use these points to find the value for h, L, and the radius of the sphere. How do we accomplish this? What kind of geometric relations can we construct with the given information? We have an expression for the center of the sphere, and we also have 3 points that are located on the surface of the sphere. With this information, we can generate a relation for the radius of the sphere by using the center in one of these points. It turns out that we can actually generate 3 relations that represent the radius of the sphere. It can be seen that the radius is equal to the length between point P and C, which is also equal to the length between point Q and C, which in turn is also equal to the length between point R and C. Since all of these relations represent the radius of the sphere, we can equate all 3 expressions together. This is similar to the law of sines that you learn in your pre-calculus or math analysis class. Recall that you can equate any 2 relations with each other in order to solve a specific expression. By using the distance formula in 3 dimensions and using point P as point 1 and the center C as point 2, we obtain the following expression for the radius. In the same manner, we can find an expression for the distance between point Q and point C as follows. Simplifying the expression, we obtain the following. And finally, the distance between point R and the center C is expressed as follows. Simplifying the expression, we obtain the following. Since all of these expressions represent the radius of the sphere, we can equate all three expressions with each other. We can make the expression more user-friendly by getting rid of the radical, so we go ahead and square all three expressions as follows. Next is just a matter of solving the system of equations. We need to solve for two distinct variables, in this case h and L. We can also generate three equations from the given relations. This is more than enough to solve the system of equations. Let's start by equating the first expression with the third expression. Let's avoid using the second expression for now, since it contains two binomials squared. We want to work with the simpler expression first. Notice that when we equate the first and third expression, we can eliminate the h squared term, since it appears on both sides of the equation. Next, let's go ahead and expand the binomial squared. Doing that, we have the following. Notice how we can also eliminate the L squared term, since it appears on both sides of the equation. Next, we go ahead and add like terms, moving the constant on one side of the equation, and the terms with the variables on the other side. Doing that, we have the following. Finally, we go ahead and solve for L. Doing that, we obtain L equals 12. Now we need to equate two distinct expressions and substitute this value for L and solve for h. Let's equate the first and second equations together. Next, let's go ahead and replace the value for L with 12 and simplify the expressions. After that, let's go ahead and expand the binomial square. Notice that the h squared terms cancel out, since it appears on both sides. Then it's just a matter of getting all the terms with the variables to one side and the constants to the other side, and simplify the expression. Lastly, we go ahead and solve for h. Doing that, we obtain h is equal to -7. We now have the center of our sphere. To find the radius is just a matter of substituting the values for h and L into any of the three line segments, since all three of them represent the radius of the sphere. Let's go ahead and substitute them into the expression representing line segment PC. Simplifying the expression, we obtain the square root of 257. So the equation of the sphere that is located in the xz plane and that passes through the points P, Q, and R is represented by the equation the quantity x plus 7 squared plus y squared plus the quantity z minus 12 squared equals 257. Alright, in our final video on three-dimensional coordinate systems, we will go over how to graph equations whose domain are restricted to a given interval.